Alright, suppose we have the Fourier series of some function f, such as this one. In this video, we show that this Fourier series converges uniformly if the series of its coefficients, such as this one and this one, converge absolutely. So that means if this is positive infinity and if this is positive infinity, then this converges uniformly. And also that if this Fourier series converges uniformly, then it converges to the function f itself. So let's start. Now let us move on to the main topic of this video, that is the uniform convergence of Fourier series. So here's the lemma. Let f be a absolutely integrable function with period 2 pi with Fourier series satisfying this. And from 0 to infinity, an is convergent, and from 1 to infinity, bn is convergent. So a and bn are the Fourier coefficients of the Fourier series of this function. Okay. So if these two conditions are satisfied, then the Fourier series S of f converges uniformly. With respect to x, any x in real. Okay, and in particular, the Fourier series is continuous, is a continuous function. So let's prove it. Okay, first of all, let's prove. The Fourier series is this. 1 over 2a0 and the sum from n equal to 1 to infinity and an cosine nx and bn sine nx. So these an and bn come from this Fourier series. Okay. So now based on this, consider this series 1 over 2 a0 plus n plus 1 infinity, the absolute value of an plus the absolute value of bn. Okay, and cosine and sine, they are bounded between plus minus 1. So this an, absolute value of an, is greater than or equal to this term, and the absolute value of bn is greater than or equal to this term, bn times sine nx. So that means this is a dominating series of the Fourier series. Okay, and by the given conditions, this one, that means this series converges. So that means the dominated series, that is this Fourier series, converges. And also note that this dominating series here does not depend on x. So that means the convergence of this Fourier series is a uniform convergence. So we have proved the first part. And so uniform convergence is proved. And about the continuity, we can see that all the terms in the Fourier series, they are continuous functions. So sines and cosines, they are continuous functions. So when a series converges uniformly, the continuity is inherited. Therefore, the Fourier series is a continuous function of x. And we are done. Okay, next lemma. If all the Fourier coefficients coefficients of a function, say f, which is periodic and absolutely integrable, all the Fourier coefficients of 0, then so that means that is this integral, negative pi to pi, and f of x cosine n of x nx dx is equal to 0, and this one sine nx equal to 0. So all the coefficients are 0. Then fx0 is equal to 0, where x0 is any continuous point of f. Okay, f is not necessarily a continuous function, so it can be discontinuous at finitely many points. But as far as the continuous points are concerned, this should be equal to 0 if these are true. Okay. In addition, if in addition f is a continuous function, so if this function f happens to be a continuous function, it is a continuous function, then in this case f of x is identically equal to 0. So it's a constant function. So that means if we have some information about the Fourier coefficients, so in this case it's a very strong condition, all of them are all the coefficients are 0. In that case, we have some information, we can get some information about the function, the original function f at its continuous points. Okay, in that that is, it's always 0 at those continuous points. Okay, so let's prove this. First of all, this x0 is nothing special. So by shifting x0, let's see, x2, x minus x0, we can always set, without losing generality, f x0 should can be just 0. Okay, we may assume x0 is equal to 0. So there's no loss of generality here. Okay, so we prove by contradiction. Okay, so suppose f of 0 is not equal to 0. And in particular, let's assume it's positive. Okay, and we're assuming f is continuous at x equal to 0. Okay, so that means by the definition of continuity, since f of x is continuous at x equal to 0, this is by assumption. Okay, so there exists some delta that is positive, such that if x actually this should be, maybe I should write x minus 0 is less than delta, then f of x minus f of 0 should be less than f0 of divided by 2. So this can be any real positive real number. So we, in particular, we just pick this positive number. Okay. So this is guaranteed if we assume f of 0 is positive. Okay. Now, by the triangle inequality, we have f of x, maybe f of 0 minus f of x is less than or equal to f of x minus f of 0. But from this is less than f0 over 2. So by rearranging this inequality, we have f of x absolute value is greater than f of 0 over 2. Now let us define a helper function. This is a bit technical, but it's helpful. So p of x is defined as 1 plus cosine x minus cosine delta. This delta is this delta, okay, same delta. And we are assuming that x is between negative and positive pi. Okay, assuming this, if x is less than or equal to delta, then cosine x is greater than or equal to cosine delta. That is because of the cosine function. Let's plot this cosine function. Cosine function is so around, let's see. So cosine function looks like this. And let's say delta is here and negative delta is here. So if x is between plus minus delta, then cosine x is greater than cosine delta. So this holds. Okay, so this means 1 plus cosine x minus cosine delta is greater than or equal to 1. So that means by the definition of p of x is greater than or equal to 1. Okay, next, if x is greater than delta, or less than negative delta, then that means cosine, wait a minute, first, negative 1 less than equal to cosine x, and that is less than cosine delta. So x is somewhere here. In this case, cosine delta is greater. Okay, so from this, we can see that if you add 1 and subtract cosine delta from everything here, then we have negative cosine delta and p of x less than 1. And of course, negative cosine delta is greater than negative 1. So that means the absolute value of p of x is less than 1. Okay, now let's consider the power of p of x. P of x to the power of k. This is up, so p of x is this one. So if we calculate the power of this function, then this is a polynomial. of cosine x. Okay, so that means it contains powers of cosine x, something like this. Okay, and however, this cosine x to the power of k is a linear combination of some constant plus cosine x and cosine 2x up to cosine kx. So C0, C1, C2 up to Ck, there are some constants. We can always express powers of cosine x in terms of this linear combination. Okay, this can be easily proved by, for example, using mathematical induction and combined with some trigonometric identity. Now, to this equality, multiply both sides by f of x. And so f of x cosine to the power of k, then integrate over this interval, negative pi to pi. Okay, so this is c0 times f of x plus c1 cosine x times f of x and so on. So all these integrals are 0 because of the assumption. So we are assuming all the Fourier coefficients are 0, so these are zeros. So this integral becomes 0. Now we split this interval into two parts. So this is equal to when x is between plus minus delta. So this part is just this part. And when x is greater, the absolute value of x is greater than delta. Maybe we can put here. Okay. Okay, for the first part, x is between plus minus delta, and we have seen that p of x is in this range. P of x is greater than 1, and also from this one, so x minus 0 is just x. Okay, so for this interval, we have this. Well, actually, since we are assuming that this delta is sufficiently small and we're assuming that f of 0 is positive, we can actually get rid of this modulus sign, and we can assume that if x is small enough, then f of x is greater than f0 over 2. So we may assume this. So going back to this integral, so the first part becomes this greater than 2 and 1. So p to the power of k is greater than 1. So dx. Just a moment. So excuse me, this is not this, but x between plus minus delta, and the second term, just leave it as it is. So if we integrate this part, then we have f of 0 times delta plus x greater than delta, and f of x p of x to the power of k. Now let us evaluate this integral. Okay, so first of all, if x is in this range, so if x is between not 0 but delta and pi, then we have as we have seen before, in this case we have this. So p of x is bounded by 1. So that means f of x, p of x to the power of k, is dominated by f of x. Okay, so this is a dominating function. And furthermore, by assumption, f of x is absolutely integrable between plus minus pi, and of course it is absolutely integrable in this interval. So this is finite. And also, if we take the limit k going to infinity and f of x and p of x to the power of k, since p of x is less than 1, this converges to 0. Okay, and when x is greater than delta. Okay, so we have a dominating function that is absolutely integrable, and this function converges to 0. That means this limit k going to infinity and this integral x greater than delta f of x p of x to the power of k dx. So we can swap the order of limit and integral by Arzeller's theorem. Okay, so we can swap the order, limit f of x p of x to the power of k dx. So Arzeller's theorem, and this is 0. So this limit is 0, so integral of 0 is 0. Okay, now, so we have this is equal to f0 of delta. And of course, we're assuming f of 0 is positive. This is by assumption. And delta is positive. And so, but this integral is less than 0. So that means we have 0 less than this, which is greater than 0. Okay, so this is a contradiction. And therefore, f of 0 cannot be positive. Cannot is not positive. And if we assume f of 0 is negative, and we can just swap the signs and do the same argument, this is also impossible. Therefore, and you should check that, therefore this must be equal to 0. And we are done. All right, now we are ready to prove the following important theorem. So suppose Fourier series of f converges if converges uniformly. Then S of f of x0 converges to f of x, where x0 is any continuous point. Of f of x. And in particular, in addition, if f of x is continuous, then we have f is equal to s of f. So f is equal to its Fourier series itself. Okay, let's prove this. Actually, the proof is not so difficult if we use that lemma we have just proved. So let us define g of x as the Fourier series of f. That is this: 0 and n from 1 to infinity, an cosine nx, and bn sine nx. And by assumption, this series converges uniformly. This series, Fourier series, converges uniformly. So that therefore, g of x is continuous everywhere. And also, term-wise integration is allowed. And term-wise integration is allowed. Okay, so let's take advantage of this. So from this, if we multiply both sides of this by cosine n and integrate between negative pi and positive pi, we have g of x cosine nx dx. So if we do this, we have pi an. And similarly, we just use the orthogonality of the cosine and sines. And similarly, if we multiply both sides by sine nx and integrate, we have pi bn. So this is because the termwise integral is okay to do. Okay, now we combine this with the Fourier coefficients of f. So by definition, uh, we have this f of x times cosine nx dx equal to pi an. So this is how we defined an and bn to begin with. And sine dx. So by subtracting both sides, this and this and this and this, we have this. So f of x minus g of x times cosine nx dx equal to 0. So this minus this, the right hand side is 0, and also f of x minus g of x sine nx dx equal to 0. So we have this. But by the above lemma, so consider f minus g as one function. Then that means uh, f of x0 minus g of x0 is equal to 0, where x0 is a continuous point, is any continuous point. point of f minus g. So f minus g is just another function. Okay, so wherever f is continuous, g is always continuous. Wherever f is continuous, then we have f of x is equal to g of x, wherever f is continuous. So in particular, if f is continuous everywhere, then f is equal to g everywhere. And we are done. And the next theorem should be almost trivial by now. But anyway, let's write it down. Suppose f is a function that is absolutely integrable. And with Fourier coefficients, an that is absolutely convergent, and bn also, then S of f, the Fourier series of f converges uniformly. And S of f of x is equal to f of x, where x is any continuous point of f. So I don't give the proof of this theorem, but you can just review what we have done in this video and just combine all the results, and I think it should be easy to prove. Okay, anyway, so let's see one example. That is this one. So if we calculate the Fourier series of this function, which we have dealt with before. This is, so before it was like the Fourier series of this function, so this was tilde here, was this. Cosine x over 1 squared plus cosine 3x over 3 squared, and so on. And x is between negative pi and pi. But now, if we apply this theorem, we can see that this is actually equal. So the Fourier series of this is equal to this function itself. To see this, the coefficients are this. So 1/2 and, okay, 1/2. So this is A0. And A1 is 4 over pi squared, and A2 is 0, and A3 is 4 over pi squared and 3 squared, and so on. Okay, and the series of these coefficients is like this. So the sum, an. So let's consider this, and that is 1/2 4 over pi squared, 4 over pi squared, 3 squared, and so on. So that is 1 over 2 and 4 pi and 1, 3 squared, 5 squared, and so on. So this converges. Therefore, according to the theorem here, we have this equality. So therefore, this Fourier series is equal to the original function itself. And we're done. Okay, that's all for this video. See you later.